And as I said, when we make a mistake, then this mistake might have different kind of consequences. And so we can actually categorize these mistakes into two different types. Okay, so we have a type 1 and type 2 errors. So this one is a true label, and this one is a prediction by a model. And when the true label is positive, then if the prediction is positive, then it is true positive. When the true label is positive, but the model says it's negative, then it's false negative. If you are not familiar with positive and negative, then just you can use just the 0 and 1 and 0 and 1. Okay, it is class 0, and we classify this one to class 0. Okay, and the false positive means when the true label is negative, the model says, oh, it is positive. Then it is false positive, which means it is false. Okay, but the model says it's positive. So this positive and positive here, and the negative, negative, negative here. Okay, and in this case, it is negative, but true means it is correct. True means correct. And the false means is not correct. Okay. So type 1 error is about false positive. It is negative, but the model says it is positive. And type 2 error is false negative. Okay. And the false positive is also known as false alarm. And given this table, we have a couple of evaluation metrics. First one is accuracy. Accuracy is, let's say this one is the number of the samples. Okay, so we have lots of samples. Then let's say we can have 30 samples and 70 samples, but we can have 15 and 15 and 50 and 20. Okay, we can have the number of samples in this table. Then the accuracy is the sum of TP and TN, TP and TN. So, which means this sum is the number of correct prediction. Okay, and total is total number of samples. So this one is accuracy. And precision is TP over TP plus FP. So this one is numerator and this one is denominator. Okay, so the precision says when the model says it is positive, then how accurate it is. Okay, and the recall is kind of the opposite of this one. Recall is TP over TP plus Fn. So this one is numerator and this one is denominator. Okay. So it says among these positive samples, how many samples the model says it is positive. Okay. So that's why we say we call recall. Recall means the model can detect these things from the samples. Okay. So I hope you understand the meaning of these evaluation metrics. And F1 score is actually 2 times P times R over P plus R, which is actually a harmonic mean of P and R, precision and recall. And when the class is balanced, which means we have around 50 negative samples and 50 positive samples, then in this case, this one is well balanced. Then accuracy is enough to evaluate your model. But sometimes we have 99 samples and 1 samples. Okay, we have 99 positive samples and 1 negative sample. And in this case, if your model has the accuracy of 99%, that is just garbage. Okay, even with the high accuracy, the accuracy is 99%, but it is just garbage, because no matter what it is, if the model says, oh, this one is positive, then the accuracy is 99%. So in this case, the classes are not balanced. So imbalanced class has some problems with accuracy. So in that case, F1 score would be more proper way to measure your model. Okay. And when you read some papers or textbook, sometimes you might see this RC curve and AUC. Okay, so let me explain what these are. Okay, RC curve shows the performance of binary classification as its discrimination threshold is changing. So basically, we have a two-dimensional space here, and this one is false positive rate, and this one is true positive rate or recall. Okay, and this one is perfect classification. It means we can recall all the positive cases. Okay, we recall all the positive cases, but we don't have false alarm. False alarm is 0. So this one is perfect. Okay, and this one is a random guess. Think about this one, this point. The recall is 0 and false alarm is 0. It means, all the time, 100%, when we say, oh, this is not a cancer. Okay, when the model says this is not a cancer all the time, then we cannot detect any cancer. So recall is 0. And also, when the model says, oh, this is not a cancer all the time, then there's no false alarm, because there is no alarm. Okay, but if we increase the threshold, then recall would increase. Okay, that's good. But at the same time, the false alarm would increase too. So when the model is just random, okay, again, when the model says sometimes positive, sometimes negative, just randomly, okay, the model is nothing. It's just random selection. It says positive or negative, half and half all the time. Then the recall would increase, and at the same time, false alarm would increase. So this is another extreme case. Look at this one. This says, the model says all the time, this is cancer. Okay, if we are here, the model says this is cancer all the time, then definitely recall is 1. The model can detect cancer all the time, but model says it is cancer when he doesn't have cancer. Okay, so false alarm is 100%. So this random guess makes this line, and if your model is helpful, then it should be something like this. And if your model is better, then it should be like this. And this one is better than this one, and this one is better than this one, and this one is better than this one. So to measure the performance, sometimes we use this area under the curve. And your model is just random guessing, then the area under the curve is 0.5. So if your AUC is 0.5, your model is just random guessing. Okay, and then your model is getting better and better, then this area is getting bigger and bigger. So finally, if AUC is 1.0, then your model is perfect. Okay, accuracy is perfect, recall is perfect, and there's no false alarm. Okay. Okay, so in the previous slide we talked about the misclassifications. Okay, so we were interested in the misclassification rate, but as I said before, some misclassifications might have different consequences. So we're gonna put more weight on some specific misclassification. So we actually put a cost value. So for example, when we classify medical images as cancer or normal, then there is a different kind of cost. So truth is cancer and the prediction says, oh, this is normal. Then this is serious. This is a big problem. So we put a lot of cost here. But when the truth is normal, then the prediction is cancer. Then this is not free. This is not zero, right? So when the true label is normal, but the model says it's cancer, then we have to pay some money to take more experiment, or we might feel some emotional kind of terrible situations. So there is a cost, but compared to this one, this cost is way much smaller than this one. Okay. So in this case, it is better to make fewer type 2 errors than type 1 errors. Okay, this type error is much cheaper than this one. Okay, so we have to avoid this error than this one. Okay, and think about an extreme case of this loss function. So if loss function is 0, 1, 1, 0, then we are only considering misclassification rate, right? So there's no difference between this one and this one. And if it is correct, then there is no cost. Okay, now when we have cost, then different costs for different types of errors, then we can calculate the expected loss. Okay, and in that case, our goal is to minimize an expected loss or risk. So this one is expected loss, and the expected loss is a sum of, and we have two summation here, and k goes from, if it is binary classification, then k goes from 0, 1, and 2. Okay, we have two classes, and j goes from 1 and 2. Okay, and if we don't have this part, okay, and then this one is exactly the same as this one. Look at this one, p of mistake from the previous slides, and in this equation we don't have loss, and other than that it's exactly the same. Okay, and to minimize this loss with respect to rj means when we change the classification, when we update our model, then the boundary will change, which means we change the regions for classes, and we should minimize this one for each x. So for each x, means we have input space, and for each x, is it R1 or R2? So we have to decide. Okay, then we just calculate this one. If it is R1, then what is the value of this one? And if it is R2, if x belongs to R2, then what is the value of this one? So depending on this one, these values, then x will be classified into 1 or 2. And considering the product rule and classify X into class J, which minimizes the conditional risk, okay, as we did here. And if we do that, then this one is base risk. So this one is the minimum risk that we can achieve, okay? And this one is conditional risk. Okay, let's take a look at this figure one more time. And this figure is from the previous one, from the misclassification rate slide. And if we don't have any if we don't have different the cost, then the boundary should be this one, right? The x naught is the best boundary. Okay, then if we have different cost, then we have a coefficient here. We actually put more weight. So putting more weight means we're actually multiplying this one. So if we have more weight on the second class, okay, then this boundary should move to this one, right? If we have more weights on class 2 like this, then this should be the boundary. Okay, so we actually shifted the boundary based on this weight. And we talked about the loss functions in the previous slide, but in general, in machine learning, we have lots of different loss functions, okay? And loss functions are objective functions to represent cost for an event. Okay, so we have a couple of popular loss functions here. And let's say let t be the target value for the estimate y. Okay, y is the value that the model generates. Okay, and the quadratic loss function is this one, also known as squared error. Okay, and mean square error is, by the way, is this one. This one is mean is coming from here. This one is average, so it is a mean squared error. Okay, and this one is quadratic loss function. And the 0, 1 loss means when the class is correct, then it is 0, otherwise it is 1. So it's just simple. I is simple indicator functions. Okay. And the hinge loss is defined by this one. And cross entropy is really popular for classification. So we're going to talk about this one in detail later. Okay. And we just talked about expected loss. So this graph actually compares a couple of different loss. Okay, so this yellow one is 0, 1 loss. Okay, so if when the target is 1, then y is negative, then loss is 1. If y is positive, then it is 0. Okay, so that's 0, 1 loss. How about hinge loss? Hinge loss is this one. Okay, so it is 1 minus t times y. So in this case, let's assume that the target is 1. Then it is max 0 and 1 minus y. Okay, so if y is negative, then we have a lot of loss. But if if y is 1, then the loss is 0, and if y is greater than 1, then it is negative. Then Max says, oh, this should be 0. Okay, so this one is hinge loss. So hinge loss says if y is not correct. Okay, so when the t is 1, then if y says something else, then we have a loss. And if y is smaller than 0, then still we have more loss. Okay, but if y is greater than 1, then it doesn't matter how large it is. the loss is 0. Okay, that's hinge loss. Okay, and then square root loss is something like this. This is quadratic function. When we use probability, sometimes we use maximum likelihood, and sometimes we use maximum a posterior, or sometimes we can use base risk. Okay, so this is a summary of a couple of previous slides.